She had a lot of stuff going on with her parents.
And her daughters too. She
And
would go
she still
visit.
got us all 4s and 5s on the AP test.
What a wonderful person.
All right, so today we're going on to chapter 3 about quantitative variables and how we can deal with those. We deal way more with quantitative variables than we deal with categorical variables. But with quantitative variables, there's no intrinsic way to make piles of data the way we did with categorical data, right? With categoricals, we had counts. How many are in this category? How many are in this category? How many are in this category? And so a bar chart worked really well. With quantitative, what we usually do is we divide up all possible values into equal width bins, then count the number of cases that fall into each bin. This is called a histogram. You've done this before. That displays the distribution at a glance by using bars whose bases are the bin values and whose heights are the counts. This is from a 7th grade pre-algebra test.
Hey,
Oh my gosh, that's us.
we might have taken that.
Yeah, that's why I was like, you should remember this.
We remember it.
Yeah,
I feel like I do. It's been a minute, but
yeah, you've slept since then. So note that unlike a bar chart, in a histogram, there's no space in between the bars. Okay, unless there's a gap in the data, like right here. Also notice that, say for this one, this is all values including 9, but not including, halfway between those two would be 10.5. It doesn't include 10.5. You always include the lower value, not the upper value. Okay? When you're looking at the bins. So if we replace the counts on the vertical axis with percentages, we get what's called a relative frequency histogram. It looks the same. And we almost never do that. Provided that we don't change the bins, the shape of the relative frequency histogram will be the same as that of a histogram, only the vertical scale is different. But the shape will be the same. Tonight's reading assignment, you'll learn how to make a histogram. Although, like I said, we those of you who are, and actually all of you use that 7th grade book, you should have at some point learned how to do a histogram. Anyway, so a stem and leaf display or a stem and leaf plot is like a histogram, but it has the advantage of you keep all of your raw data. So stem and leaf displays are especially useful when you make them by hand for batches of fewer than a few hundred data values, which cracks me up. I'm like, a few hundred? A stem and leaf plot by hand? Really? That's what your book says. It just made me laugh. I was like, if it's more than 20, I'm out. Here's another example taken from pre-algebra with the weight of each girl on a basketball team. A couple things to note. There's no title or explanation of how to read the display or an indication of units. So let's fix this. So this is weights of, I'll just put BB players. In pounds. Units are important. And then we should explain, and I usually just pick one off of here. I'll do like 13, 3 is 133 pounds. So second, notice that because this display has smaller units on top, all we have to do to visualize an associated histogram is rotate it 90 degrees. So if you were to draw the bins, and rotate this puppy counterclockwise. You didn't know puppy is an indefinite pronoun?
I did.
Mrs. Freeman taught you that, right?
Did
Yes.
she did.
If you just took this whole thing and rotated it, you would have a histogram.
Oh, that's cool.
So that is one thing that's in their favor. If you have a lot of data, stem and leaf plots just get crazy. All right, the next one we're going to look at is called a dot plot. It just places a dot along an axis for each case in the data. Like a stem and leaf plot, dot plots preserve the original data, but they don't group the data into bins. It's useful at times and terrible at other times. Like, this is sort of like a histogram with way too many bins, right? It doesn't group anything together. We typically will clump, some things together to make a better histogram. So, the condition for quantitative data, if you have a histogram, stem and leaf, box plot, and I'll add dot plot to that. Check that the data are values of quantitative variables whose units are known. Right? If it's not quantitative, none of these things are good things to try. All right. Here's some stuff, and again, a lot of this we did in 7th grade pre-algebra. It is super important that you can talk about the shape of a distribution. It's going to be on the AP exam, I can almost guarantee you. Every year they ask something at some point about the shape of a distribution. And frequently they'll ask you to compare one distribution with another distribution. Generally speaking, they're histograms, but not always. So when you describe a distribution, you should talk about its shape, its center, and its spread. If you haven't talked about those three things, you haven't said enough. All right, there are all kinds of different shapes. This one is an example of unimodal, meaning you have one bin that has more than everybody else does. Okay? This one is bimodal. I have these two high ones and then lots of, it's Snow White and the Wicked Witch and all the seven dwarfs. Okay? Two things are much bigger than everybody else. And then this is the worst when you get ones like this. This is multimodal. We don't deal with this very often because there's just not much you can do with it. You're like, well, it's kind of all spread out all over the place. Occasionally you can make those better by making the bin widths bigger. But even then, a lot of times they just end up being ugly. And you can't do very much analysis with them. A histogram that doesn't appear to have any obvious mode, like all the bars are about the same height, that's called uniform. Again, you don't see that very often. Another part of the shape is whether or not it's symmetric. Meaning, if you look to one side and to the other side, are the two sides about the same kind of a shape? So for example, in that unimodal one, it's unimodal and at least fairly symmetric. It doesn't have to be perfectly symmetric, right? That's one of the things that sometimes drives, really good math students crazy about statistics, is a lot of times we're like, yeah, that's good enough. And in math, it's like, we don't like that, but it happens a lot. So can you fold it along a vertical line through the middle and have the edges match pretty closely? Or are more of the values on one side? So this is actually, I took this from Wikipedia. This was their example of symmetric distribution. Notice it's far from perfect, but it's basically symmetrical. There's about the same values on each side of the middle. Note that this is also unimodal. Bimodal and multimodal can be symmetric, but it's less likely. So the ends of the distributions on the left and the right are called the tails. If one tail stretches out farther than the other, the histogram is said to be skewed to the side of the longer tail. And this is one where it's easy to get it backwards. Whether we're right skewed or left skewed is all about where the tail is. It's not where the mode is. And I know this is one, when I first started looking at it, I did it backwards several times. I mean, it hasn't been that long ago that I learned all this stuff. And so I did it wrong multiple times. So here your data is right skewed. Here your data is left skewed. Part of it is that, you know, if we're looking at the mode, like the mode here is in here, but since there's so much data over here, it would pull the mean up. So that's part of that right skewed. It's pulling on the mean. Outliers can also skew data, but that's another subject. So here, this is symmetric. I would also say that it is sort of bimodal. Here, this is skewed. It's unimodal.
That one would be left skewed, right?
Yes, this is left skewed, because that's where the tail is. Single peaked, and I took this right out of your pre-algebra book. We usually don't say that. We usually just say unimodal. Now, when we talk about symmetry for this one, I would say it's slightly left skewed. We'll a lot of times hedge our bets. We'll say it's, you know, strongly, slightly, somewhat, right? We'll do that a lot. Again, double peaked, we usually call that bimodal. And this one is actually fairly symmetric. And this last one is an example of uniform, where it's like, we're not going to be able to do anything with this data. And that's why you just don't see very many of those. Is it perfectly uniform? No. But is it pretty close? Yeah. All right. So the next thing is, do any unusual features stick out? You should always mention any potential outliers that stand off away from the body of the data. If we were to make a histogram of the ages of the people in this room, there would be an outlier.
Bro.
Yeah. Because Aaron's pretty close.
No.
Oh. I get it. I get it now.
And I do this in my pre-algebra class. It's near the beginning of the year. Every year, we figure out, you know, I'm like, so let's look at the ages of the people in this room. And my class this year, every stinking one of them is 12. Every one of them is 12. And they're like, yeah, that's going to be easy. We can find the mean, we can find the median, super easy. I said, but every person in the room, they're like, oh. The median is still 12, but the mean got to be, I think it was like 15 and a half or something.
Really?
I'm like, I really, really, really skewed the mean there.
Yeah.
Okay, so here are a couple of pictures. This is pretty clearly an outlier. We will define ways, actually there's two different ways, but we'll define ways of identifying an outlier a little bit later. Okay, this is, I would say, it might be an outlier. I don't know. Maybe it is. There's definitely a gap though. Okay, and sometimes an outlier, it's just your data, like something went wrong. Sometimes it's like, oh yeah, we said people, not students, and so we have to count Mr. Davis, and so he's an outlier, right? So sometimes it's informative, sometimes it's wrong, but you never just drop a piece of data because it looks like it's an outlier. And occasionally when you're going through the analysis, you'll analyze it with the outlier and then do it again without the outlier. If you're going to do a complete analysis, if you're like, there's an outlier and this is how it affected it, you need to talk about it completely. All right? Sometimes when there's a gap, there is no outlier. When there's a really big gap, you can be pretty sure that's an outlier. All right, so the center. Most of the time we're going to talk about the median when we're looking at histograms. Why? Because if you're looking at a histogram, you don't have the original data anymore, right? But you do have the counts. So you can figure out where the median is. So I don't want to do any of those. But here, you could figure out where the median is in this horrible, horrible data by counting up how many total are there, finding the middle one. Remember, if there's not a middle one, you can average those two together. And a lot of times on these, since we don't have the original data, you would have to say the median is in the 15 to 17 and a half bin. You won't know what it is exactly, but you'll know where it falls on this. All right? So that's median. All right, spread. There's a couple of different things we can talk about for the spread. One of them is the range. The range is the maximum minus the minimum. Okay, note that when we talk about range, it's a single number. It's not an interval. Sometimes it is helpful if you're writing a description, you can say that the ages ranged from 12 to 62, right? As opposed to saying the range is from 12 to 62. Range is a specific value. A lot of times when I'm analyzing, data from a chart or something, I'll give, the range of values went from, or it ranged from this value to that value to give people more context. Okay. A better way to describe the spread, and by the way, if there's an outlier, you get this really big range. Well, is there, in my 7th grade pre-algebra class, is there a lot of difference in the ages? No, there's just one really big difference. So a lot of times it's better to look at what's called the interquartile range. We did this in pre-algebra also. Okay, it's been a long time. So to do this, we divide the data in half with one group consisting of numbers above the mean, and I'm sorry, is that the bell?
Yes, sir.
And that'll be above the median, and the other half below the median. All right. We won't have a new lesson on Friday, but on Monday, we won't spend as long going over homework, and we won't tell as many fun stories.